So good evening everyone. Today is the third week of the lecture and I'll be covering today the application part, or I will start some of the application part and I'll solve some numericals also. So today will be more like practicals and numericals of till now whatever we have studied, and very little theory. So let's start. So again we'll revise few of the topics for radar imagery. Just we'll go through quickly for this slide. Like we have already saw that the radar equation, we studied about this. We have to remember, okay, this is the radar equation and what are all the components: that transmitted power, gain, range, radar cross section. These another important formula regarding SAR or radar is this. This is, you can say, this is the equation for signal to noise ratio. So from the radar equation we can get this, because we are more interested into calculating the maximum range we can get, or we, for that radar we shifted from real aperture radar to synthetic aperture radar so that we can increase our range resolution. This is also another beam width related formula. We saw just how it worked. I'm going through quickly through the equations because we'll discuss few numericals today. So just to remind you the equations, we also studied about the two types of resolution, and all that range resolution and azimuth resolution. And in range resolution there is two types: the slant range resolution and ground range resolution. So this is the slant range resolution formula, c tau by 2. This is the, you can see the diagram, what it is actually slant range and ground range, and why this is PL, this PL, why it is important. See, tau is pulse duration. So this is, it is actually the length it is traveling. So here it is showing the length it is traveling, and by 2, why it is PL, or total the length it is going here, and I mean it is repeating the distance. So by 2 we will get only one distance, and that is the real distance. It will not get doubled. What is meaning, I mean, does it mean by pulse length? These all slant range or ground range, why, what are these? We already saw these things. How do we, I mean, convert to each slant range to each ground range? That depends on each pixels, you can say, incidence angle, slant to ground. These are the different terminology: depression angle, look angle, and this is finally the equation for slant to ground. So there the theta, or this is the incidence angle, the theta comes in the role when converting from slant to ground. So these things we will see today in practical also, in a software, in practical also there these terms will come and you can connect then. this thing, these two images are important to understand. So slant range versus, so we, as SAR is side looking, so there is two terms we already discussed. This is the near range and far range. So this, suppose this is the flight, and it is looking from here to till here. So this is called the near range and this is called the far range. This one. So it is looking from here to there. So what, so basically here we are forming the image. We are getting some received signal or received pulse, can say received power. From that power we are generating images. So what happens, suppose it is going from here to far and it is getting elongated normally because we are taking the slant or ground. So it gets elongated from here to there. So from how far it goes, the object's impression or image, we will not get the actual impression because we get the elongated one because we are looking from here to there. The angle here, this angle is decreasing. That's why these things, slant range, this looks like this. You can see these are very compressed and middle one are good one, and this is also again compressed. And when we detect, or I mean project it to ground range, it, the pixels or it all are same pixels. By 2 again, and azimuth direction it is fixed always. So azimuth resolution it is there, beam width and the slant distance. Here comes, so till now we already studied in the last week and I went through quickly because today we will solve few numericals. We'll see few numericals based on these equations. Next comes the SAR. What happens to the SAR image? Different distortions. Okay, for when we capture optical image, we deal with optical images, optical sensor based images. We deal with mostly the atmospheric phenomena, atmospheric corrections are very important when dealing with optical images. But for SAR, it can penetrate through clouds and these things. So, atmospheric, these interference are not that much big issue. But other issues are there. One of them is the geometric distortions. Different types of distortions we get. So, when SAR has different domain. When we deal with SAR image, we have to consider few things. First of all, noise and clutter. These things we will cover in coming weeks. These things are very important to understand, and different distortions because SAR has different looking phenomena, different capturing procedures. Because of that, what distortions we actually face? It is called the geometric distortions or relief distortions. Relief means some height. So distortions regarding height. Okay. Suppose, here look at these only image. You will get many images and we will not able to differentiate between these type of distortion. There is three types of distortion: layover, shadow and foreshortening. Any one of them happens based on the terrain. So from the name you can see relief distortion. Relief means some height. So more the height, distortions will happen more. One of the factors. And I mean, people who work in application field, there, if their site is more terrain, hilly area, they get this type of distortion, this type of issue to solve very, commonly. But normally, if we are working in a city level, and depends on the pixel or resolution also, in a city level or flat terrain, it is not that much an issue because it depends on the height. So suppose this is our flight, and here these all the types of phenomena are explained in one. So this is the flight, and from here we are looking to the terrain. It has different location and different these height objects. So first of all, suppose it is getting here to here, taking the swath. It is the swath width. So capturing here to here the signal. So first of all, suppose here some height objects. What it gets, what received signal it gets. It gets here, hits here and all the here, and it gets the all these are the projecting to this line and here. So we are getting this portion and this total portion return. And if we plot this to ground, to a flat, slant to ground range, so we'll get this portion as layover. It is called layover, and this is as weak return. Okay, because this portion, this face, it can't see this part. So second, if we go here, so it is called, here the layover is happening, the shadow. So shadow coming later, layover. So layover happens when these points, it gets elongated. The image or that face of the object gets elongated. So this face, it gets elongated. And the shadow region is where we don't get any signal, received signal. It is totally dark. Okay, that is called shadow. We don't get any signal from that region. And next comes here. So here it is totally shadowed region, because this part, it is totally, if we project this part, it is totally projected, this type of object totally. So this is totally off in SAR image. This is one shortcoming you can see. Next comes the foreshortening. What happens in practically, the object or that area gets shortened. We actually, it is of the size, we get the shortened size of it. So when it happens, when the target or the point in academic terms, we call it when the point is away from the its face, its front face. So that's how this face gets shortened. The actual projection, we we need to see it gets shortened by this, and rest of this part is totally shadowed region. We get no signal from this part. So these are the phenomena we get, and this kind of, when hills and hilly terrains are there, so we can see, or we can't differentiate which one is really a hill or which one is really the other part, or what to say, that person. So it is very deceiving nature, but there are ways to decrease or to handle this. We can't eliminate these things, we have to decrease these things. These are the three types of distortions. what happens with the foreshortening. So you can see the same image. I mean, these two are the same image, but it looks so different, and because of layover, it gets very elongated. I mean, stretchy, and because of the foreshortening happen, so it gets compressed, very short distance and sorted. These are the things happens. This is the another image if you want to understand the layover and foreshortening. This is the layover, it gets elongated, and this is the foreshortening, this part. Sorry, this is the layover, this is the foreshortening, this is the shadow area. So this type of images appear. So you, I mean, practically if you imagine, lesser the incidence angle, or I mean more it gets elongated, the shadow increases. So that is another parameter also, for depends on the terrain totally. So it is said that as incidence angle decreases from near to far range, so will shadow effects, as the radar beam looks more and more oblique at the surface. So from here to there, it, as I said, it increases from near to far range because it is side looking, and so shadow effects also increase to the far range normally. So that is why, I mean, normally we don't, I mean, consider, or if our sight suppose lies on it, suppose it is one tile we get from in a sensor, if our site lies, or our intended area of interest lies somewhere nearby the boundary of the tile, okay, edge of the tile, so we don't take that normally. We take another tile where it comes in the middle portion or little bit, not the edge portions, because their distortions are so much more. It is better to get another tile and take little, because we can't eliminate those distortions totally. It is another motion compensated and motion, I mean non-motion compensated, that is the original, and motion compensated image. So SAR, I mean, it is a moving flight, and the signals and everything we are getting, so we get this type of noisy and grainy image because of the motion and different type of motion of the antenna, that is raw pitch, yaw, this are called defined xyz in 3D coordinates, different types of motion. Because of that, these things happen. I'll cover that in noise, or when I'll discuss the speckle, noise, clutter in detail in coming weeks. And so after some filtering, you can say some corrections, we get this motion compensated image. So these are all are different distortions, and it is not like we have to do always all the corrections to every image. It depends. If our image is that much affected to that kind of distortions, we do that. Normally SAR needs one kind of speckle filtering, that is because SAR is very much affected by that, but not to these, all these. It depends on our objectives. Then comes resampling. It is, I mean, I think I will skip this. Then comes this multi-look. Very important to understand. It is very much important mathematically also. So look. What is look? It is each of the sub images used to form the output summed image implemented in the processor. Okay. So single look image use all signal returns from a ground target to create a single image. Image will contain speckle but have the highest achievable resolution, and independent images of the same area can be formed in the digital processor data by using subset of the signal returns. And these images are then averaged to create a single multi-look image. So not that much, I mean it is only theory, multi look what. One thing is we have many resources. I want to share you resources from where you can let me see screen. If you search, you can get many of our tutorial, this PDF, but which to look, you will get plenty of. Now SAR is so famous and processing Sentinel-1 data, but you better you look to authentic in resources. You get the from authentic source also proper. So this is one from ESA, the European Space Agency. There the Sentinel-1, this satellite is there, so they publish this toolbox, and there these are the handbook. I mean whatever we are reading or studying, these are very crucial to understand that in practically. I directly, I mean giving you or showing you this because so that you can later access these things and also read. Here you can see the multi looking, they have explained. Okay, actually what is multi looking, what range and azimuth, why, I mean, how it is happening, these things. So normally what we get, single look image, that SLC image, single look complex image. It is called the SLC image. It is one look image and with phase. Single look complex image is the raw file, that is phase image and also single look image. There we are getting, suppose for one type of sensor data, this range azimuth spacing, but this is this. We need approx at least most of the square pixels. Okay, so for that it depends on the incidence angle. So we will basically multiply these and these to certain numbers and will try to get the degree. So you will wonder how it is going to work. It is not like that. I think it is not given here properly. So I will show you. One second. Okay. So from that also I think better I show again. This multi-looking concept you can read from here, and some other also pre-processing steps are, all the pre-processing steps for Sentinel-1 or for any SAR image are explained here. You will not get any good guidebook or any good PPT also like that. These are all the official handbook, and better if you follow these things you will understand what is called calibration of data, why do we do this multi-looking, another type of pre-processing, then speckle reduction, all these, terrain correction. Look here, it is explained for certain these geometric distortions. What are these? Slant to ground. So how it is dealing? What are these? So these are very official and very authentic source to get the information. And if search, you get the PDF online. So next I will so next I want to just discuss few numericals based on the radar equation and also two three more equation, range, azimuth and radar equation. If you are interested, you can um, try by your own. These are very based, straightforward based on the equation, but when solving these numericals, it is better to look at the units. Units are very important. Units conversion, to understand units, what are the all the units for different parameters different. So if anyone wants to try these later, you can. I will discuss one by one. These numericals are very important because blindly just processing in software or in Python, we don't really understand physically what a radar does and what we are doing. The basic, we don't need more. So many things are there in the radar real things, but that part, this hard part, if we know the numericals, we can visualize many things when processing or when, and we can solve the many issues also. So first numerical I'll be discussing, it is based on first few numerical based on this radar equation. It is called radar equation. So the received power is equal to transmitted power into gain of the antenna by 4 pi range, that is r square, into sigma, that is cross section, by 4 pi r square, into the effective antenna aperture area. All are given here. So the numerical, it says the one radar system, it is transmitting power of 50 kilowatt, antenna gain is given, it is constant, range is given 100 kilometer, radar cross section is 2 meter square, and effective antenna aperture is 0.5 meter square. So calculate the received power. Simply, it is very simple, straightforward, but we have to focus on the units. We have to convert the units to kilowatt to watt, to kilometer to meter. Okay. Then if we just calculate these, and finally what we are getting, here it is said we are getting some watt power, 1.58 into 10 to the power minus 16 watt, or minus 158 dB watt. So what, when we, I mean, people do actual experiments, suppose lab experiments with radar and what they are getting, so we will not communicate with these big numerical terms, okay, digits, that okay, how much you are getting, I am getting 1.5 into 10 to the power minus 16. No one can understand what, how much actually it is. That's why we, as I said before also, we use the dB version here, dB watt more, because things come this much, these in these digits, 10 to the power minus 10, 10 to the power minus 16, like this. So watt to dB watt converts, I think equation next it is given. Now you need to remember few conversion these units, that 1 watt is equal to 10 to the power, suppose 1 dB watt by 10. So if we do that, here we will get this minus 158 dB watt. So when suppose solve for any exam, yes, we solve till this watt, we are not giving this dB watt, so it is not enough. Next is, if one radar receives minus 140 dB watt power from a target at 50 kilometer range with a radar cross section is given, effective antenna aperture is given, and calculate the product of the transmitting power and antenna gain Basically this one is it is asking for. So we will adjust the equation accordingly, the same equation, and then continue. So here again we get the this. So this is the watt, and we or approximately 1 megawatt. So these are the conversions few we need to know. These are straightforward very. Again, to calculate the radar cross section of the target, another is given. So transmitting power is given, gain is given. We are converting all the in respective units. dB watt to watt. We will not work with dB watt directly. So radar cross section will calculate that in meter square will get. So 2.81. Finally, this is the thing we calculate the maximum range using the maximum range equation of the radar equation. So these are the given transmitting power, all these. So maximum range, if we adjust the equation, it comes like r to the power 4 is equal to this. And accordingly we calculate, and it is coming, you can see, approx 90 kilometers. So you can understand how much, I mean, the SAR is covering actually. Another thing to understand from this maximum range equation, I can tell here, it is r to the power 4 is equal to the transmitted power into all these. So r to the range increase in fourth power of any of these. So among these, antenna gain is constant, radar cross section you can say you take it as a constant, antenna effective aperture area also constant, and received power accordingly. So if we suppose double the power, how much it will increase? It to the 8th power of the range. So it increases in that degree. You have to understand this, because practically it has significance. It gets increased to the r to the power 4. Next, some numericals on signal to noise ratio on this, based on this. So what is signal to noise ratio? If we want to understand that in layman language, suppose I mean, there are, we all have seen, why it is like this, we all have seen the GPS we are using in mobile. We are using from mobile. So why we do use the total station, all these things? We can use the GPS. Why those instruments? Okay. So because our mobile does not have that signal to noise ratio that one total station has, or one GPS station those has. So it has very high signal to noise ratio. So for a radar sensor, that matters very much, because noise is a factor for radar, or SAR better say. So there we are interested to this S minimum. Okay, the minimum signal to detect, or detectable signal, minimum detectable signal. So sophisticated radar system requires a minimum signal to noise ratio of 15 dB for reliable detection. The system operates with a bandwidth of 5 MHz and has a noise figure of 4.5 dB. If the system integrates 64 pulses coherently, calculate the minimum detectable signal power in dBm at standard temperature. Okay, it needs in dBm. It is not like you will calculate anything in any unit. So we will convert all these 15 decibel to linear, these 45 to this bandwidth also megahertz to this hertz, and number of pulses is given. So S mean, it is direct straightforward. We'll calculate all these in watt. So convert these in dBm. These are nothing but the 10 log of, it has the equation. It is not shown here. I will share this PPT with you. I will sharing the slides. You can follow and you can check the numericals in the PPT. Next, another numerical. It is asking for required number of pulses at standard temperature. So radar, it has, it says its minimum detectable signal is minus 130 dBm. So and they converted it to watts. So you need to know the dBm to watt conversion. It is giving here. Then all are other are given, and it is getting this, and it gets, so number of pulses in point. Okay, so it is getting one digit 127.3. But pulse means the wave. Suppose one sine wave total. So it can't be in partition, na? I mean 127.8 with point 0.3. What is the point 0.3 pulse? So they round up to next power 2. So we will round up to higher side. Will not do the lower side. Will not do the 127. We'll do it 128. Okay. So the system needs to integrate 128 pulses to achieve the minimum detectable signal. Now comes the based on numericals based on the range and azimuth resolution. So we'll see, for azimuth resolution the equation is this. Okay, range into lambda by d, and for range resolution it is the constant c by 2b or c tau by 2, whatever, depends. B is bandwidth. So for range resolution it is given a SAR system with a chirp pulse having a bandwidth of 150 MHz. Calculate the range resolution, and if the bandwidth is reduced to 75 MHz, what is the new resolution? For two types of bandwidth it is asking. So not always it will give you the pulse length. So you have to know the relation between bandwidth and pulse length also. Okay, so see the range resolution, it is r is equal to either c tau by 2 or r is equal to c by 2b. So you will get also the relation between beam width b with tau. So you will just megahertz, and you will get, I mean 1 10 to the power 6 hertz, and you will get the respective. Now comes the thing next. Radar needs an azimuth resolution of 100 meters at a range of 15 kilometer. So it operates at a wavelength of 2 centimeter. So we need the required antenna length. This is where the SAR comes. Okay. So as per the equation, this equation, range into lambda by d, So we will arrange, and so D is the antenna length. Okay, we'll get the 3 meters. So the antenna must be 3 meters long to achieve the desired resolution. So one thing to see, it one 3-meter antenna and in other parameters are like this. It needs the azimuth resolution is 100 meters. It is so high in the sense, so lesser, coarser resolution. We deal with the, I mean, suppose 5 meter, 10 meter, 15 meters resolution, and here it is saying, and for 100-meter resolution this much coarser, it still needs 3 meters antenna length. So next is one system, it has the maximum range 25 kilometer, operating frequency is given, maximum allowable antenna length is 1.5 meter. Now calculate the azimuth resolution at 10 kilometer range, and when the range is 10 kilometer, maximum range is 25 kilometer, but they are asking you to calculate when the range is 10 kilometer. And also azimuth resolution at maximum range, that is 25 kilometer, and if the resolution at maximum range needs to be improved by 40%, what would be the new required antenna length? This type of a little bit complex problem. The first two are very much straightforward, that is calculate the lambda from the frequency and light of speed, then calculate resolution at 10 kilometer, that is the range into lambda by d. Second at 25 kilometers, similar, but for 40% improvement at 25 kilometer, new resolution will be this. New desired resolution is 200 meter. So for the new resolution, you have to calculate the antenna length that is there. So just do step by step. Next, I have given 4 multiple choice questions, and it is not multiple, I mean multiple and are correct. Multiple options can be correct and a bit tricky, I have said. You can try on your own. If you have any doubt, you can ask me regarding. I mean, these 4 questions only I have given, and these you can think about these questions. Better to think, better to understand, better to search also. These are much more conceptual questions, and multiples are correct. These 4 questions and numericals also, I'd be happy if you solve by yourself and mail me, or any other doubts also you can ask. Next comes the hands-on. So till now today, I think the theoretical parts are over. I will show you different data, different products on softwares, few processing, very basic level processing. So first I mean, this course is, I mean, we'll be using the ALOS Pulsar 2, ALOS 2 data. So first you have to understand, you have to know your data in remote sensing, and it is very important to know your data and constantly read about your data. It is not like, okay, data is ALOS 2, we don't know anything what is ALOS 2, its background and its specifications, at least from where to get the specifications. We need those resources also. So this ALOS 2, or it was named Daiichi 2, and it is operated by Japan, or JAXA, Japan Space Agency, given by Japan Aerospace. So they called it, named it Daiichi, and it is the Daiichi mission, all the mission, and there ALOS 2 is there, ALOS 3 also, all there. So operated by JAXA, Japan Space Exploration Agency, and it started in 2006. Okay, and ALOS mission started in 2006, not ALOS 2. Okay, and ALOS 2 particular few specifications better to know. What are the type? It is sun synchronous type. Okay, altitude, it is moving there. Inclination angle, revisit cycle. This is very important. Every 40 days, it has very high revisit period. But still, we are very interested because it is L band. It is very high wavelength band. It can penetrate few degree, and it comes with single pole, dual pole, and quad pole also polarization. And I have shared in these two links also. I'll come these after. These are the different things to know. Otherwise, you can't read your data. Resolution. So Pulse Allos 2, Allos Pulsar 2 has, I mean, if you want to buy the data, which one to buy? These so many specifications you will get. Which one will be your target? You need to know what actually spotlight means, strip map mode means, cancer means. Okay, so all the resolution it has different. So strip map has three different resolutions for ALOS 2. The ultrafine, that is 3 meter, high sensitive 6 meter, fine 10 meter, all these. Then cancer comes. So spotlight, I think in the first lecture I told you the spotlight, the strip map, the cancer. Spotlight needs very much power. It is only spotting at one area. Strip map is the swath I mean it is moving, and cancer also, but cancer has very lower resolution comparably, and its focus is to cover larger area. So cancer cover larger area, but resolution you can see it is mostly 100 meters to 60 meters, where in comparison to that, to strip map covers comes in suppose 3 meter, 6 meter to 10 meter. Incidence angles, very important. It varies from 8 to 70. Okay, all these. Swath also. You can see the swath, it is the cancer covering. So these cancer is very important when you are, I mean, you need to process, you are more interested towards regional or country level processing, country level findings. Okay, polarization, what is this? Is SP means single pole, DP means dual pole. So these all are given is the, if you, I mean, before I have already given the link, the product guide, it is called allows to product guide. Always read from the authentic, whatever the JAXA has published, not just downloading, anyone is telling anything, anyone is giving anything from official site. Just read the product guide, only read from that. So it is, these are from there. Single pole, dual pole, and compact pole also, and full pole, fully pole, FP. These are the short terms, I think here it is given. Rest are not that much. Range azimuth it is given, not that much important. So here the same in the product guidebook also they have given all these for basic level understanding, what it is strip map actually, how cancer works, how spotlight works. Okay, next comes the calibration factor. We need to calibrate our data. Okay, calibrate means the digital number in the pulsar 2 juxta standard product is converted to backscattering coefficient, that is sigma naught, sigma 0, using the following equations. These are the equations. The sigma, here it is the backscattering coefficient, sigma naught or sigma, it is called sigma naught. Dn value is digital number, and it is CF is calibration factor. And for ALOS 2, it is here minus 83, and A is 32. It depends in anything for SLC image or level 1.1. I will come, I think that I have shown. Yeah, different levels of product. So and I and Q are the, I mean, complex number. So that um, product. So I mean, I is intensity, Q is the phase. Okay. So these are the different level of products we get. One point. So I mean, if you are going to purchase or download this data, allows to data is not, it is commercial data, it is not open source, you have to purchase. If you want to order that, you have to mention, okay, which level product you want. You will not get all those things. One tile of, suppose, level 1.8 depends on the area also, 100 square kilometer area and 500 square kilometer area. It cost you 2 3 lakhs, starting from 2 3 lakhs, depends on the how much area, which product. Is it, you do you want terrain corrected or not, all those things matter. So different levels of products are there: 1.1, 1.5, 2.1, 3.1. And what does that mean? So level, it is the raw data. 1.1, that means no pre-processing is done. Range and single look azimuth compressed data is represented by complex I and Q channels to preserve the magnitude and phase information. Okay. But 1.5 range and multi-look azimuth compressed data is represented by amplitude data. Here there is no phase. Okay. So these terminologies we need to know. And these also I want to, these things, you, if you click, I have given two links. You can go to this JAXA, this is their site, Japan site, and there you can just explore all those. See, in the ALOS mission, that is the Advanced Land Observing Satellite, they have so many ALOS. First ALOS, these ones started in 2006, and then ALOS 2, ALOS 3, ALOS 4, different. It has different. Every ALOS mission has different uh, target. So ALOS 2 is more towards disaster monitoring. Okay, agriculture monitoring, more towards this. ALOS 2, you can read about the overview, you can get the sensor. So how does it look actually? These are the antenna, and read about those. I've shown you only this much. All those you can get PDFs, and you can get sample products also. If you want to just try or just test your learning in software, you can get sample product for free from here. All those things. So it is better to explore or know these resources from here and just study. And next one is the product guide. This is the handbook to when you actually start working. If you buy any product, they will give you this. I mean, it comes with the product guide, and it's still loading. You will get all the details of your product, whatever. If you need anything, all the details here. You just explore. what. So I have already, these are the contents. So you'll get all the, what are the products, and so I have given the just link. Next I will come on the processing state. So I will show you data and also processing on software, that is called snap. You just snap, I think ma'am already showed you. These are all the backscatter, and we will see now what are these sigma naught, or this is the backscattering coefficient or intensity. So we will see from where to download Sentinel-1 data, how to download. We have some LOS2 data. So with that, I will show you few things and basic pre-processing. Now, I will if you want to download Snap, it is freely download, and just type ESA, European Space Agency, and just type Snap. This one step, download step, and here you just click there, download Snap. Here you can whatever you want according to your system. This Sentinel toolbox is smooth. You, I mean, better to just download this. So you will get the snap data from this site, their ESA site, European Space Agency, their site. It is freely available and install, very easy software. And now I will show you. This is the interface. And always check for the updates and don't block any updates. Always update, allow updates for your snaps. Otherwise it will not give you, I mean, the processing, it will give error, all those things. We already downloaded data. Okay, I will show you from where to download the data. It is called Alaska Satellite Facility, ASF search. I think better to ASF data search. These things you have to know, and here you sign in using your ID, these things. After logging in, search type, search for now, search this geographic search data set. Now you can see the Sentinel-1 data. Sentinel-1 started in 2014 till present. ALOS Pulsar, it is the first ALOS mission. It is not ALOS 2 mission because these are the open source data. So ALOS first mission, it uh, started in 2016 until 2011. That time data is available. SARC data also another. Rest, if you want to explore, you can explore different UVSAR. Radar Sar 1 data, another SAR data, that also was another mission, 1996 to 2008. All these data. Sentinel 1 data, if you suppose choose this. Now you will get this. You can draw by yourself. Suppose I am drawing was in Delhi, any of these, or you can upload any safe file also, kml file, all those, starting date, anything give. Now go come to filters. Here you can understand now all about whatever we read about SAR. Okay, first area we selected, data date we selected. Now additional filters. If we click this, you will get these many options are coming. That is L1 detected high resolution dual pole, GRD, that is ground range detected. Here comes the L1 level 1 single loop complex that we read, SLC, and others these things also. So we are more interested on this GRD data and also this data. Beam mode. Normally we work with this IW, interferometric white. This is also another thing. I mean, you can just, I mean, SAR has many terminologies. You will get every terminologies, and you just search and just read 2 3 lines about this. What does it mean? IW, polarization. So here it is central one is dual polarization, single and dual. So VVVH or HHHB, whatever. We are just not selecting anything, whatever it gives. Descending, ascending and descending. So it, I mean, the according to the this it is central one has 7 days revisited cycle. So it goes, then it comes back like that. So ascending, descending. Sentinel has these two. I mean, ascending, descending, Sentinel A, Sentinel B, these two. And also, if you want to the just path and frame, if you want to, for now I will not. I'll show you what is path and frame. Just search, and you can get these many tiles in the date from 1st January to 31st January. Here we are getting these many tiles. All are SLC data also, GID data also. So here you can see the path, the frame. So you can specify particular one path and frame. Just this zoom. You will get different dates, different path and frame. Suppose this path and frame 2792. This has different path and frame. So the satellite passes on different path and taking different frame. The same path and frame, suppose if we want to look at the 2792, we will just specify here we want to look at this path and frame. We get these three. Now you can see these three are the same path and frame of different dates. Okay. How to download? Suppose if you want to download this one, click and just click to the cart. I've already and from here download this. And better also, if you want to download through Python, download this Python script. It is downloaded. If you want, just go take the where you want to download, just go there. If you want to download from bulk, there. There you, or you can search cart and you just download that. So we download the data. I have already downloaded Sentinel 1 and allows to data. We have data, purchase data. I'll show you just. And Sentinel 1 data, you will get zip file, then unzip it and you will get these files. And this file is the important. So in Snap, what do many people just drag and drop the files? Don't do that. That by that many from data many few components, and it shows error many times. Better to just import the data in proper way. From file import, there are many these formats. So SAR format, SAR sensor, these all are SARs and you can explore. We will take Sentinel 1. See, we have this. We will import the safe file dot safe import product. It is importing, you can see here, and it is imported. Now just open this. It has all the metadata, vector data, type point, grids and bands. I will just show you one by one to read. Metadata, abstracted metadata. You can see these all, whatever we read, these all are about the mission, about the capture of the data. Everything is given. What are the polarization, VH, VV, and all those terms you read, many those terms you will get here. And the bands, these are the we downloaded SLC, the level 1 SLC product, single loop complex. It comes with amplitude and phase both. It is raw product, so we get raw bands. So in VH, it I is the real number and Q is the phase complex number, the imaginary number. Q is the imaginary part. So VH, in the VH wave, the suppose I plus CQ. So is the constant. So I is the intensity or amplitude, Q is the phase. So we are getting this product. And intensity they are given again. These are the amplitude I. Again for VV it is given. Okay. And different swath, IW1, IW2, IW3. It covers it 3 swath. We'll see the swath when processing. It takes like this 3 swath divide. So for 3 swath, the same for different area. So we have imported and opened the product. Now we will do some pre-processing. We'll show pre-processing, or we will generate intensity image, suppose. So for Sentinel 1 pre-process data pre-processing, we have to, and if you want to see, suppose, the intensity image first. it is creating the image. Okay, so we have to know, what it is creating. For IW1, the SWAT 1, it is creating the image. We'll just see. It is, there is no pre-processing done, nothing. See, now it looks like this. I mean, total it is not coming. Yeah, it has lines. No pre-processing. I mean, no multi-looking, no terrain corrected, no speckle filtering, and these are the lines that comes in the raw file of SAR. Okay, all those things. If we look at the intensity, look, this is nothing. We I mean, SAR image is this. Unless until we process this, we could not see anything. Is it visible to really? It is so stretch, and still if you want to see all, I mean, you can't really identify anything that it is Delhi image. So now we will see some pre-processing, and we understand also simultaneously that what are those processing. First we study about, we will go to radar, that is the toolbox, and we will um, take the Sentinel-1 tops, and we will do the Sentinel-1 topos split. Here suppose these are the processing parameters will go. Now you can see these are the swath. The three swath it is giving 1, 2 and 3. So suppose I am interested in 2 second swath, and we are just selecting the two bands. It will very fast. It will not take that much time. After this, I will tell you how to do at a stretch. Still, this is taking time. It is done. So we'll see this. So split is done. Then we will do the apply orbit file. It will select the orbit, or it will specify the orbit. We'll keep this as it is. Just run. So these are the very, I mean, standard pre-processing steps for Sentinel-1. Sentinel-1 data comes with those strips and SWAT, and you have to, I mean, if you, I mean, check the guide also. Suppose in the, I mean, here in this PDF, here they have specified all these. You can follow this also, that what to, this is for Sentinel-1 by European Space Agency, what they are doing. So first, still, I mean, these are not that authenticated. I am showing you in practical purpose. If you see any tutorial, there you will get the those terms. So it is done. So now it has specified one orbit, that okay, this data is for this area, it's specified. Now we'll do the calibration. So for Sentinel-1, these two steps we have to do always. For LOS2 data, we no need to do this. Now we will do, that is in radiometric calibrate. We will calibrate our data. Now here one thing to check. These two bands we will select, and this. If you want to save as complex output, that is the same as IQ, and sigma band, that is the backscatter, that is the dB, that is the intensity, sigma intensity, or gamma also, or gamma band also, or beta band also. You can take any of these. Normally we work with sigma, but you can check this. And also if you are working with phase, that is the other polarimetry or these things, then we are more interested into the complex output. For now I want to show you the intensity or the sigma dB. So we will take this output of sigma. We'll run the product. This is calibration is very important, and allows data processing, pre-processing starts from this calibration, that I will show you also. Allows 2 data. Here we are processing dual polarized data, dual band. It has, so this data has VV and VH band. Sentinel-1 data. Meanwhile, if anyone has any doubt, you can always ask, because these are the practicals tutorials, and if anyone has any queries. So calibration is done. Now we will go to deburst. It is called deburst. So that lines you saw na, it will go now to with this deburst, and it is important for Sentinel-1 product. These are the pre-processing steps for particularly Sentinel-1. So that we will get this, you have to use to Sentinel-1. Look here, these are the specified only for Sentinel-1. We will do the deburst. Again, better to select. Ask regarding software, regarding data, regarding anything. It is done. Now we will do the multi-look. So the orbital split, calibration and deburst done. And now we have suppose one image, but it is not multi-look. We got the sigma band for the swath 2 for 2 bands, VH, VV. Look, their lines are gone. If you check calibration. Look, the lines are there. When we do the debust, then lines are gone. But it is stretched. I mean, it is not multi-looked, it is single looked. We need to set the pixel size. So we'll do the multi-looking. Here all the things are at a click and it calculates on its own. If you check here the multi-looking, it will do on its own. Look, it already took 4:1. We will multi-look our two bands. So see here it is mentioned ground range square pixel. So we are doing the ground range square pixel. Automatically it calculates to 4:1 and it will give us to these pixels 14.32 some. We get this, and after getting this we can resample it. We can upsample, downsample, depends. And also we can specify any of our independent looks based on our requirement. So we will multi-look this, and here it is said output intensity. And read these notes also, whatever is coming. One note is given: detection for complex data is done without resampling. So when you work with complex data, there the resampling or their processing is procedures are different. Multi-look we have done. Now we will do the thing speckle filter. These all are the pre-processing. I mean, if you, whatever task you want to do with Sentinel-1, you have to do these things first. Now some speckle filtering we have to. So speckle, we have not read yet about speckle, noise, clutter, but for this, for now just do that. There are different type of filtering: boxcar, medium, Lee, refined, Lee sigma, whatever. We select refined Lee. Okay. If you select, you get defined window size also, target window size, all those things. Next, the last process is always terrain correction. That is, now we will do the geometric terrain correction, range Doppler terrain correction it is called. See the input, output, all the things. Now parameters, here it is to see, look at. Suppose bands, these two, we are interested. The digital elevation model, we can use external DM or any auto downloaded DM that normally we use in SRTM. 3 second, that is the open source 3 second, that 30-meter DM. We use this, but for better process also we can use external DM if you have higher resolution DM. Now the resampling method, bilinear, cubic, nearest, all these are the thing. So we normally take as it is. Image resampling method similarly as it is. Now see, it calculates the ground, range and azimuth, or better here it says azimuth and range is this meter, 13.9 approx 14 to 14.6. So we are doing this. After getting this, we will resample, and also map projection. We can select to project UTM. suppose UTMWG is 84. Okay. It automatically zone 43. Delhi comes under zone 43. So it took. Now different options are there also. Mask out areas without elevation subject source band. DM, if you want to save some this external incidence angle from LS side. Many times we want to use this file latitude longitude and other files gets layover shadow mask. Many, I mean, which people they work with the layover shadow and speckle, they, I mean, filtering, different filtering process, they get this layer. And also these are the different apply radiometric normalization. You, I mean, there are so many things, you just go through and search, okay, what it is, it is doing. So normally we do this, keep it as it is, then we'll do the trend correction. It takes a little more time compared to others. So till now, and you can see how the naming goes. So you keep it as it is. Okay, the speed, vital calibration, reverse, multi loop, then speckle, then terrain correction. It will come. And name your file like this, and also try to read your name. I mean, ma'am already these things shown. I mean, I am not telling everything. I mean, it is not possible. You have to things learned by yourself. Check that, okay, what does this name means. So these are the dates. I mean, the nomenclature you have to understand. This is the interferometric weights, SLC data, the name. It is the date for 16 this July and these things. Now we will see the intensity band output, final output terrain corrected, and see. Now you can see the Delhi. Okay, two bands, the VH band and VV band. I mean, for VH it is the H sends transmitting H and receiving V. For V it is the transmitting V and receiving the same V. For Delhi region, we are looking at the middle, this swath, and this is the Yamuna river going. For date 16 July 2023. Okay, particularly why I am showing you this style, there is a reason. These are the flooded. Okay, on this date it was flooded. So if you see the VH band, suppose these two, I mean, we will cover later on why these two are different, why, what does it mean on VH, why, what does it mean in VV. But at a glance, I have shown you these black things. It is Yamuna river and it is flooded. Okay, and side by areas are also darker areas appear as flooded also here and here. It depends. And VV also things. So that's why I showed you particular this style. 16 July Delhi. This is the Delhi per person. So now if you read the metadata, you can see the ascending descending paths. Now you can save this and export view as image, full resolution, GOT, just save. And we will see this overlapping and the values also in QGIS. to simply we will drag and drop this here in QGIS, zoom to layer, when open the satellite, it is projected on over Delhi, and you can see the Yamuna river, whatever it is going on. This in non-flood situation you can very easily understand or look at that. Okay, it was not the normal time, regular time river, it is flooded, it is Delhi. So this is the different value. See, if you see band, it is saved as 3 band. These are the intensity values. Okay, range from 0 to 255, it is scaled, different intensity value. Here very less. This is how we process in Snap the Sentinel-1 data. For doing any task, this is the pre-processing steps. These are the pre-processing steps. Now we will see allows to data. How to? That is very less. We will go to import SAR, similar SAR sensor, allows to COS format. GeoTips, when you purchase allows to data, they will ask you which one. You have to specify which one type of data you want to. GeoTIFF, they will make the image and give you your COS. We prefer COS, that is the raw file, level 1 COS file, because we can, after that we can do whatever we want with that data. Here we will import the volume file. The volume file has all the data. In Python also ma'am showed that we import volume file. In Snap also we import the volume file. Now these are, suppose I am closing all this. Now the allows to data I have imported. Check the metadata allows to data. I have imported one quad pole data. Okay, this is quad pole data for Japan. So from the starting, if you, these are the incidence angle, near range, far range. It lies, I mean, from 37.6 to 40.3, okay, degrees. And that long pass, it is ascending pass. And here you can see the 4 bands. It is quad pole data. In Sentinel, there if you check the metadata, it showed you only 2 bands. Okay, VH, VV. For allows to data, quad pole data, this has 4 bands, HH, HV, VH, VV. And it is the single look, I mean, no processing has been done. So 1:1 it is saying. And range and azimuth spacing, now you can see it is, range is 2.8 meter, azimuth is 3.1 something, these meters. And this data is 6 meter resolution. Okay, 6 meter fine resolution data. We saw that there is 3 meter ultrafine, 6 meter resolution, 10 meter resolution in strip map mode. This is strip map, 6 meter resolution data. So we will process this. It has very simple procedures and bands also. Now see here also similar, the real and imaginary parts and intensity they are given, if you see. But for 4 here it is quad polarized, that is fully polarized data in 4 bands. And these data it we purchased, and it cost for one tile, you can say for one tile it cost around this much area, 3 to 4 lakhs it cost. Okay, and it is one flooded area, that's why we purchased. So we will proceed process and better see that. We process better. So first we'll do the calibration. For sentinel, we did the split and orbit, apply orbit, specifying orbit. But here we'll start with calibration. Simple calibration, multi-look and terrain, speckle filtering and terrain correction. So we'll do the calibration. Radar, radiometric, calibrate. So we will specify no, it is the allows to data, select processing parameters. Look, we will select, we will not select all, we will select only real and complex. Either, or if we want to only look at only the intensity, we will select the intensities. For now I am selecting the intensities only. Here also options come, save as complex or save in dB, that is the sigma naught in dB. This video will be on YouTube. You can later also check this, because in product guidebook also many tutorials you will get parts of this. Not the actual, okay, these are the pre-processing steps you can do one by one. Because whatever I am telling you, these are from the practical experience. It will take some time because the data is little bit larger. Meanwhile, if you have any doubts, anything, you can ask. Yes, hello. Yes, yes.
Myself are one.
Okay.
I told the basketing geometry in the starting of the classes. How to best getting reflected in the terrain, different terrains.
How does the backscatter reflects in different terrains?
Yes, ma'am.
Question.
You know, ma'am, you explained how to the best getting best scattering in different terrain. It also urban areas also do like it's happening like that, or otherwise because the urban area the building orientation and building density are the difference.
Okay.
So how it's best getting affected in urban area.
Actually, that part, that different, that comes under when we discover the polarization. That is the VVVH. We that will coming in. I mean, later week. I checked. I mean, as per the syllabus, uh, that is one very larger portion, one domain. For now, I that whatever I mentioned today, that is for geometric distortion. That is not backscattering. Okay, that will happen for anywhere, depends on the height relief. But whatever your question is, oh, yes, that is the, I mean, now we work and in practical application field, those are the things we are interested for, that in urban area and agriculture, these things, how these backscatter, these VH, all these things are, how these are, I mean, interacting. The thing is, in one two lines we can't, I mean, tell you, but that will come in, I mean, later week, coming week, in very detail. We have not went to that okay, it depends on the dielectric, different geometric shape, the roughness, those things, and how it will uh, depend. It needs, I mean, few slides. It is not like one two slides. Roughly, I mean, there are many scattering terms, that is surface scattering, volume scattering, double bound scattering, all those, helix scattering, many more terms. So those terms will come, then we will understand in graphically also, that okay, in urban, I mean, to say for now, in urban, it says that double bound scattering happens. But what is double bounds? In which type of structure it happens? Okay. For now, if you want to understand, you, for this data, quad pool data, you see the four bands. These are the four bands, maximum bands we can get: HH, HB, VH, VB. So for urban, this area, this HH and HB, these two are called the volumetric, or the dihedral scattering. So that these two bands are sensitive for in urban area. Okay. So we, I mean, now it is difficult to make you understand, because I mean, without showing any picture or anything, why it is. But that syllabus and that will come in very detail in later week. Okay, and I'll cover that part in very detail. For now, I mean, different in urban, it happens in volume scattering, and some part of double bond scattering, and some part of volume scattering also happens. Why that happens? What are, in what factor it happens? So all those, that is very complex, and but we'll cover that. We have not covered yet. We'll just starting till now. Also, we have not entered in the SAR. We are till now still in pre-processing stage, basic, very basic understanding, knowing the nomenclature, knowing these things, what are the channels, HH, what does it mean. Because later on we will, I mean, many more other terminologies will come, then these things will be very basic. Okay, so later on that is coming in very detailed part. So is, I mean, was your question, I mean, I got your question, but that is not, till now we have not covered that. Okay, we'll definitely cover that in detail. So the calibration is done. Next, we'll do the speckle filtering. Speckle also, I mean, we are just now understanding the SAR basic terminologies. Today I wanted to cover, but I saw that it is in next week. So clutter, noise, speckle, these things are very, I mean, SAR study without noise, without speckle, it is, I mean, not finished. So we will cover that, and then the polarizations come. Whatever questions we will saw the backscattering. What is backscattering and what different? All those things are coming. So later the speckle filtering. For now, just check. Okay, speckle. Check this. It already came. You can see that in DB. It is normally the till now the latest. So we these things, I mean, snap, and I today wanted to just give one just basic demonstration so that you can start by, I mean, on your own. You can, I mean, start in Python also, as ma'am said, and I will show you also in Python, but I prefer both. I mean, you check in Python also the same, in Snap also. But there are differences. I mean, the results you will get, you might get different, definitely. You might get same also. It is, I mean, intended to, obviously the same procedures you are doing same, but you will get different results. Why those different results you will get? All these things to understand. And Snap is very handy. I mean, whatever we are studying so many things, but we can't visualize. For that, basic starting software is very good, and Snap is on the spot stuff software. For at processing also, we many times we process in Snap also. Python is okay, but for starting and for understanding things, to visualize at least something, the software is one stop solution. It takes some time because data is a lot. And meanwhile, I want to tell you, if, I mean, there are sites you can download, the ASF Alaska Satellite Facility site download. But there are sites for to purchase the data also from JAXA portal, JAXA G portal it is called. That is, I mean, operated by Japan, obviously. They, from there you can search allos products, allos 2 products, and we purchase from there. We can purchase from there directly. You can select and you can add to cart, and you can just specify the order, all those things. And there are many mid uh, seller, you can contact to them. Last is we will do the terrain correction, that is range Doppler terrain correction. Why do we call it range Doppler terrain correction? That is also one thing to understand. It automatically to, it is UTM, it is Japan UTM zone 54. Okay, we will run. I'll just show you the results. Today we are just showing you the intensity. But when you told that, okay, backscattering, which, what is, when polarization or polarimetry will come in scene, then we will work with only complex phase things come there with intensity and phase, or amplitude and phase, both these two things come there. We don't calculate the dB or the sigma. There we calculate or out take the output of complex output. So this is the last process, and I want to show you another data processing steps in Snap that is very useful. Here you are doing one by one. I mean, you have to sit in front of your PC and do these things with time. Suppose you have to process 10 data. So you are sitting there and doing this. No, there is one option where you can select that and just make that, and it will be automatically done. It is also one flooded data on Japan that happened in 2019. So there we can see a little. So the processing completed. Let's see how the images come. Suppose HH image come like this, HV, VH. When we will study about the polarizations, then we can understand better these images. Okay, for now suppose HH. So all these things came. This is how we in Snap software we process the allows2 data, Sentinel-1 data. And here also similarly export view as image and full resolution we can view in QGIS. Similarly, that I am not doing now, no use, it is in Japan. So okay, I wanted to show you the graph builder. There is one option from tool to graph builder. There is, if suppose you have to, I mean, process a lot of data, or at least these so many for Sentinel-1, so many steps, and also other many steps are there also. There you can simply just make your data line and like this. Suppose here first you want to add split, then radar, same options you will get. Suppose a split, you will do this, then from here you will connect this, it will get connected. Similarly, next also you will suppose something, apply orbit file, you will get, you do this, do this. Similarly, you make your flow chart, then from the last chart the right, you have to, it is the output, this is the input output. So this will be your, and you can save this, export this flowchart and use for multiple next products also. No need to do one by one. For read, you can select from here which product. Output also select. For every these, you can select the swath, apply orbit file, all these things. So this is very useful when you wish to do the processing for larger data. And so we make one flowchart, save that. Here this is the save option, save that, and also there is the load graph. Next time you go load that graph and just simply do the processing. It will do the automatic all the processing, and the final product it will give you. In Snap this is very useful, graph builder. There is another is batch processing, it is also there. Same, you just import all the data here and just add all the data, suppose 10 products, then load the graph and process. This is how, because these are the pre-processing, we don't want to waste our time, much time on this. So for today, these are the very basics I wanted to show. and I have already shared the PPT or slides. You can better the 4 MCQs. I have not told you the answer, or because it is a bit tough, I said, and better to understand and search on your own. Try to solve on your own, and you can send me the answer also. And the numericals also, if you don't try, you will not, it will not get clear that okay, what is happening, what is there. And the few links you will get, I have said, it is always those are the resources to follow to get other many information, any other processing, any other queries. So that's it for today, and in the coming week we will discuss other topics as per our syllabus. So for today that's it. Any queries you can ask now, or you can mail also. I'd be happy to answer. So thank you for today.